Bismillahirrahmanirrahim. Hello everyone. So in continuation with the chapter 9, so this is second video of the chapter 9. So we have different shapes of shell and tube heat exchangers. So these are very much portable kind of shell and tube heat exchangers, as you can see in the picture. And again, you see in this picture there are several other shell and tube type of heat exchangers. So these are small scale applications, and as we know that there are very large scale shell and tube heat exchangers as well. So if you are thinking about that, what is the overall heat transfer coefficient for different types of heat exchangers having different fluids? So here is the fluid combination, like the hot fluid and cold fluid. So with this combination, that what is the expected overall heat transfer coefficient? So if you have water and water heat exchanger, and one is hot and one is cold, so your overall heat transfer coefficient will be in this range. Similarly, like for other combinations, like this is reduced crude oil and this is flashed crude oil, so the overall heat transfer coefficient in this range. Similarly, if you have light oil and water, so the heat transfer coefficient. So these are the recommended range. These are not like the actual measurements, but this is like what is the possible value for different designs or for different shapes. So it lies in this range. So there are others also, like this is for heaters, like if you want to generate steam from water, and this is for condensers. So the condenser and vaporizers or evaporators, they usually have very high heat transfer coefficient because there is a phase change happens. Um, and then comes the fouling factor coefficients or fouling resistance. So there are different fluids, as we saw in chapter 8 for different fluids. So there are different fouling factors or fouling coefficients. So these are the values of fouling coefficient for different fluids. So there are different standards for shell and tube heat exchangers. So when we talk about the tube, there are again different standards. There is British standards, there is ASME standards, there is ANSI standard. Similarly, for the tube, when we talk about the tube and we talk about the thickness of the tube, size of the tube, then there is a standard that we call Birmingham wire gauge, and that is related to the tube thickness. So these are the standard that given that the indication for the standard is gauge, like gauge 1, 2, 3, 4, 5, and so on, and corresponding to it there is a thickness of the tube, so that is mentioned here. What is the thickness of the tube? Let's say for gauge 13, if we talk about, then the tube thickness is 0.09 inches and 2.4 millimeter for gauge 13. Similarly, for other gauges, the thickness is given. Okay, so when we do the analysis of shell and tube heat exchanger, so what are the different steps? So some suggested steps are given, like first of all we take the initial decision, and then we need to take the tube side thermal analysis, then we have to carry out shell side thermal analysis, and then we need to calculate the overall heat transfer coefficient, and then the analysis, hydraulic analysis. Hydraulic analysis means like calculating the friction factor and pressure drop for the tube side, and then friction factor and pressure drop for the shell side. Now imagine if you have two fluids, one is hot fluid, one is warm fluid, one has less viscosity, one has high viscosity, one is working under lower pressure, one is working under higher pressure, and so on. So there are two fluids at two different conditions and having different properties. So how do we decide that the which fluid should we pass through the tubes and which fluid we should pass through the shell? So these are the, as you can see on your screen, so these are the guidelines to recommendations to follow when you design the heat exchanger. and this is for the tube side preferred under these circumstances. So if under these circumstances it is preferred that the fluid should be flown in the tube side. Similarly, under certain circumstances, if the fluid matches these circumstances, then the fluid should be flown from the shell side. So these conditions are summarized in the form of a table, and here we have that the general design considerations on fluid routing, which fluid should be routed through the tube and which fluid should be routed through the shell. So there are different factors. So if we talk about that, there is a corrosion is a factor, falling factor is another factor, fluid temperature is another factor, pressure drop, viscosity, steam flow rate, pressure drop, range, and velocity. So these are the factors based on which we decide that whether the fluid should go through the tube or through the shell. Let's talk about the corrosion first. So if your fluid is corrosive, then where it should be flown? So if the fluid is corrosive, then it should be preferred to move through the tubes. So the fluid which having higher corrosive tendency should be put in the tube, and less corrosion tendency should be put in shell side. Okay, why is it so? Because if you put in the shell side, then it is affecting both surfaces, tube surfaces as well as shell surfaces. While when you pass it through the tube side, it is only affecting the tube surface. Now for the second factor, falling factor. So if you have two fluid, one fluid having higher falling factor, another having lower falling factor, so how do we decide about this? So the fluid which is having higher falling factor should be flown through the tubes. Again, for the same reason that it will fall, the falling will take place only at the inner surface of the tube. On the other case, if you are routing it through the shell side, then both the outer surface of the tube and the inner surface of the shell will be fall, and the falling will take place on both the surfaces. Okay, now for the temperature. So the one fluid is hot and one fluid is cold. So one fluid having higher temperature, another fluid having lower temperature. So the higher temperature fluid should be flown through the tubes, and the reason is the one like the safety itself. So the lower temperature fluid will flow in shell side, and there will be less temperature of the condenser surface, so there will be less losses also. So there are two things: one is the safety, low temperature, another is the loss due to low temperature. The third is the pressure drop. So the pressure drop, like which fluid having the higher pressure drop tendency. So which fluid do you expect that the pressure drop will take place higher? So usually the fluid with low pressure drop should be flown into the in the tube. Low pressure drop tendency. So the low pressure drop tendency and the low viscosity, they basically walk together, because if the fluid is less viscous, it has less pressure drop tendency. So the less viscous fluid and the less pressure drop tendency should be flown in the tube side, whereas for high viscosity fluid which causes high pressure drop, that should be allowed to flow through the shell side. And why is it so? Because the shell side, usually the fluid velocity is much less than the tube side, so so the less pressure drop occurs for that fluid. For the flow rate, so the higher flow rate fluid should be flown through the tubes, and the fluid with low flow rate should be flown through the shell side. And why is it so? The reason is that the tube side, the fluid is flowing on a straight path. The tubes are straight and it is moving from one end to other end, whereas in the shell the fluid basically flow in a spiral manner, in a zigzag manner. So for the shell side, the fluid goes up, goes down, goes up, goes down, goes up, whereas in the tube side the fluid is just go from one end to another end and then come back from other end to first end. So when the fluid is having a lot of turns, then there is a possibility of that the fluid will have a lot of recirculation and a lot of impact on the baffles. So to avoid this, the low flow rate is preferred on the shell side, and the high flow rate can be flown through the tubes. Now for the pressure range, when the fluid, when you have two fluids and the two fluids, they are under different pressure conditions. So the high pressure condition fluid should be flown through the tubes, and obviously this is for the safety reason as well, that the tubes are surrounded by the shell side fluid from the outside as well, and the tube thickness can be chosen accordingly to sustain the higher pressure. Now comes to velocity, that the tube side should be maintained optimal velocity, whereas the shell side, as I said, that the shell side fluid flows at a low flow rate and with low velocity, so the economic velocity cannot be maintained for the shell flow.